And everyone, and welcome to today's webinar run by the DWHR project. And I'll provide you with a little bit more detail around the DWHR project in the coming slides. For those of you who joined us for the first of our webinar series, you're very welcome. And for those of you who are returning to the series, thanks for joining us again. And today's theme for the webinar is recovering heat from drain water, making it happen. So this is the third of our four webinars in the series that we're running over the past few weeks and then coming into next month. And for those of you who have joined us for the first time today, this topic of heat from drain water that might be of interest to you, the previous session which we've run on this topic as well, dealing with the opportunity, details of that, and the prior session on micro hydropower is available on our DWHR website. And also we have a future session coming up next month on water and energy efficiency. And at the end of today's session, we'll provide you with details and links for that. But today we've 2 hours in store, so it's great to have you all here to not just hear from our speakers, but participate in the second half, where we'll be sharing details of how you can approach assessing drain water heat recovery for yourselves. So my name is John Gallagher. I probably didn't introduce myself on the first slide. I'm an assistant professor in the School of Engineering at Trinity College, and I'm one of the research team in Trinity College. And we partner with our partner university in Wales, Bangor University, as part of an Ireland-Wales Interreg project. And DWHR is essentially, the objective is it's a scientific investigation and exploring innovative practices on improving the efficiency and the energy performance of water supply and consumption. And as you can see from the illustration on the right, we have different approaches on how we aim to achieve that. Technology platforms such as drain water heat recovery that we're going to be speaking about today, as well as hydropower that we've dealt with in a prior session, and recording is available of that session, and also smart network controls, another area that we're dealing with. But also working with our partners in Bangor University in Wales, we're also dealing with the environmental aspects, the benchmarking aspects, the energy auditing, and the life cycle opportunities to be considered in the design and the implementation of these technologies. And also with our partners in the School of Business, Trinity Business School, and we also have we're fortunate to have developed a smart specialization cluster, which is a key part of our project to bring together people with a shared interest and various levels of expertise from industry, from academia, and both public and private sectors. And we'd encourage those of you who are joining us for the first time to visit our website, check out how you can be involved in our cluster, stay informed and stay connected with the project. And we hope that you can stay with us for the next 2 years of the project. And we've been running for 4 years at this point, so we have a lot to share with you, and we hope that might be of benefit to you. So before I introduce the speakers, just to give you a little bit of procedures for today's webinar for the 2-hour session. You'll be relieved to hear that we're going to have a break around the halfway point after our 2 sets of presentations. So this session is being recorded, and it's for the benefit for you to recap and for sharing beyond this. So what I'd suggest for the presentations is to make sure that your microphone and camera is off for this session to allow focus for our speakers. But please, by all means, utilize the raise your hand or to use the chat box to pose questions. It's also a good opportunity now to maybe ask you all to make sure that your name is clear in your profile. So if you can edit that using the top right 3 dots, you can modify your name if you're coming into this, joining this with someone else's account, for example, or your name isn't clear. But also, you're very welcome in the chat to introduce yourselves to everyone today. And I'm sure some of our team is going to drop some hellos into the chat to kind of get the discussion going and introduce themselves. And some of our team are here today to participate in any questions and also to connect with you if there's anything that's maybe beyond the heat recovery topic. So that's our first hour, 2 sets of presentations with questions after each of the 2 speakers. I'll introduce the 2 speakers in a moment. And then that represents part 1 and 2, if you will. We're going to each presentations. Each presenter has a section there. And then in the second hour, we want to have an interactive session. So that part, I would encourage you to have your cameras on and then to turn on your microphones for questions. You can again put the questions in the chat and I can invite you or raise your hand, use the raise hand function. Either option is available to you. And in that part 3, we'll also share the tool that we're going to be going through, the heat recovery toolkit that we're going through in the interactive session. And we'll share that in the latter half of today's event. So let's get down to, I suppose, the reason you've all joined. And I see it's great to see that we have a nice audience of over 20 people participating today. And the specific topic of today's seminar is catchy, maybe in some ways. It's about flushing money down the drain in terms of heat recovery and the opportunity to capture what is essentially wasted energy. And our 2 speakers today are 2 members have been the 2 members of the DWHR2 team, Isabel Szestak, who is a PhD researcher in the School of Natural Sciences in Bangor University. Hi, Isabel, are you there? And
hi, everyone. Hi.
Hi, Isabel, great to hear you. And I'll hand over the next slide to you in a minute to do our first poll to get your views. And also a former PhD student and now working as a project consultant in Belgium, Dr. Jan Spreet. Jan, hi.
Hi, good afternoon, everyone.
Jan, great to have you back as now somebody who has kind of completed his phase of the project, but contributed quite a lot. So Isabel and Jan will be presenting over the next 40 minutes on their work. And after each of their presentations, there's an opportunity for questions. Please post your questions throughout in the chat or even raise your hand during the presentation, but we'll wait for the questions at the end of each presenter's session. So before we get into the presentations, I'd like to hand over to Isabel because we're going to open up with a small poll to the audience, if that's okay. So Isabel, over to you for this slide.
Thank you, John, for the introduction. Yeah, we have a little poll prepared because we would like to know of you, the participants, where you're coming from. So I'm launching a poll, which you should be able to see now. If not, please shout. So the first question is about your area of work. The second one is, does your business or your workplace have climate action targets? And the third one is, have you heard about heat recovery from wastewater before? So probably who attended the previous webinar has already some insight into this, and probably our colleagues are experts in this. I will just give you a couple more seconds.
And if for those of you who are not overly familiar with Zoom, I suppose, Isabel, you can find the polls if they haven't popped up on the screen along the bottom menu of your page, but I think they should have popped up in front of everyone's.
Okay, so I can see that 70% have already voted, but the numbers are still going up. So I will wait a couple more seconds so everybody can vote. And then when I end the polling, you should be able to see the results as well. Okay, we have reached 90%. Let's see if there's still something happening. Okay, it seems nothing's happening anymore, so I'm gonna end the polling. Yeah, so I'm pleased to see that we have really a variety of backgrounds here. Also a couple of people from the hospitality business. That's great. Okay, most of your workplaces have climate action targets in place. That's also very nice to see. And most of our participants already have heard about heat recovery from wastewater, but for some of you it will be completely new. So that's also a good mix here. Thanks for participating. Actually, could you, now you can see the results, I think. Yeah, okay, but I've gone through them. Okay, great, then let's finish the poll, and welcome to everybody from my side as well. Back to you, John.
Thanks, Isabel. And Isabel will be giving her talk after Jan in a few minutes. So before I hand over to Jan, just to kind of more specifically outline the 3 parts of today's session. The first session will be dealing with the opportunity, a presentation by Jan, opportunity for direct heat recovery in the hospitality sector. And you'll have a case study as part of that. And Isabel then will take over in part 2, looking at the environmental costs and savings of recovering heat. And it will be linked in some way to the case study as well, having informed elements of that. And so that will bring us up to around the hour mark, maybe a little bit over, but we'll make sure we have a 5-minute break before we move into part 3, which is the decision support tool, the heat recovery decision support tool, which Isabel will give a run through of, but we will also make sure to share that. And that will be a much more interactive session. Questions can be thrown at Isabel, if you will, throughout the session. We're more than happy to help guide you through utilizing the tool, both today and beyond today, and any final questions and feedback then as we close up for today. So without further ado, I'd like to hand over to Jan and to hand over control of the screen as well, Jan. So Dr. Jan Spreet, former PhD student of our team and an expert in heat recovery. So Jan, I'm going to stop sharing and I'll allow you to take over and share your slides.
That's great. Thank you, John. So I hope everyone can see my screen. So also from my side, good afternoon. And so I'll be talking about the opportunity for direct heat recovery, and mainly talk about the kitchen and hospitality sector. So we'll mainly talk about the technical aspects. So I'm sure that I don't have to introduce the urgency and the problem of the disruption of the climate to anyone anymore. So climate disruption is one of the 9 planetary boundaries, and so there are increasing climate ambitions in the EU, but also now separately in the UK. And these efforts are as well supplying clean, affordable energy and building and renovating in an energy efficient way. Heating and cooling account for around 50% of the energy consumption in the EU. So these numbers date from when the UK was still part of the EU. And so around 75% of heating energy is still delivered by fossil fuels. And then in addition to that, we see that 15 to 30% of the energy, the thermal energy that is delivered to a building is actually still embedded in the wastewater when it's leaving. So there's actually literally energy being flushed away. And that's one of the reasons why in December 2018, wastewater was actually recognized as a renewable source of heat. And so it's on this source that we are doing research. So the classical example is shower heat recovery. The water of the shower is still hot when it's being flushed down the drain. So we have this little animation here that you might recognize from the previous webinar. But we see that there's actually hot water being used when we are showering, and that is still hot when it moves down the drain. It moves through a heat exchanger that is used to preheat the incoming hot water, and thus reduce actually, let's say, the classical consumption of the boiler. So this is let's say a technology that's already in the market. It's installed in around, I think, 70,000 places across the UK. And here on the right, you can see an example of such an installation with multiples of this heat exchanger in a swimming pool in France. And so the idea that we're discussing here is actually transferring this market-ready technology to the kitchen and hospitality sector. Why do we want to do that? On the one side, because some commercial kitchens can be very large, up to 12,500 liters per day. And also the temperature of the wastewater in kitchens is quite high because of Legionella legislation. So the idea is that the cold water supply coming in is preheated in the heat exchanger before it goes to the boiler, and thus it reduces the fuel consumption of the boiler. And so it's preheated using the warm wastewater going through the middle of our heat exchanger. So we looked at that in the hospitality and food services. On the one side, because it's a large water consumer. So there was a RAP report, I think from 2013, that estimated the water consumption at around 170 million cubic meter per year, and an equivalent energy consumption of around 18 terawatt hour. So let's say 170 million cubic meter per year. That's roughly the equivalent of the consumption of all residents of Ireland. And then the total food and drink industry is around 350 million cubic meter per year. That's roughly the equivalent of Belgium, where I'm from. And so the idea of our research was to look at how much heat is still embedded in this drain water, and what is actually realistic to recover from that wastewater, both in financial and environmental terms. And so to do that, we first started with measuring the data with the monitoring campaign. And here you can see a flow profile of the kitchen of Penryn Castle, which we will come back to later, where we measured the flow. We measured every 15 minutes, but here for clarity, it's shown per hour. Why do this in a profile? Well, because if you say renewable energy, we usually have a problem of intermittency. So that's one of the things we wanted to look at, is this importance of this temporal aspects. This is not like wind or solar where we have no control at all, or where it's hard to predict. But in a way, we are not going to adapt our water use because we want to recover heat from the sewer or from the wastewater. So we observed this profile at Penryn Castle, and we saw that around 75% of this heat is hot water. Then we also looked at the temperature of the drain water in different places. So in kitchens of nursing homes, leisure centers, hotels across Wales and Ireland. And we see that we have peaks of up to around just under 40 degrees of temperature in the early afternoon. And so the idea is to reduce that temperature, to extract the heat and thus reduce that temperature as well. So we looked at the potential then in the hospitality and services. And so looked actually at the financial feasibility of this heat recovery using the commercially available system for showers. So we look at two things. It's the daily water consumption on the x-axis here. And then the heating fuel it's replacing. So fuel oil, natural gas, wood pellets. And then on the y-axis, we calculate a net present value. And in blue, we have the financial net present value. And the idea here was to look at from which threshold, which kitchen size, it would be interesting to implement these systems. And so that depends, as I said, on the current heating fuel and the water consumption. We can see here that for fuel oil, natural gas, and wood pellets at low flows, it's not financially feasible, but it still would reduce the emissions, which is the green curve. So there we then looked into developing a prototype to recover heat from there. But I think that was talked about in the previous webinar. So applying this then to the total sector in the UK, the total hospitality and services sector in the UK, we see a heat recovery potential, let's say technical, of 1.4 terawatt hours per year, of which around 89% or 1.24 is already financially feasible with this system that's coming from showers. We did that by dividing, let's say, all the food outlets in 9 categories. So restaurants, quick service or fast food, pubs, hotels, leisure, staff catering, healthcare, education, and services. And we divided those then again in 4 different size categories to look at their daily water consumption or yearly water consumption. What we didn't look at this study was to take into account the distance between the drain and the current heating system. There was no way for us to estimate whether or not the vertical drop was available to actually install this heat exchanger pipe. And our system is not feasible at small flows, which you can see by the, let's say, the orange upper parts. That is technical potential, but not profitable potential. And what one of the important aspects here is that we can recover this heat at an estimated price of around 6 pence per kilogram of reduction in carbon emissions, if we assume a 10-year lifetime. And then if we compare this to the classical example of renewable heats, which are heat pumps, we are several degrees, several orders of magnitude smaller than actually installing a heat pump, for example. So for the people who are more interested in this was published, so you can find more details there. But then let's move on to our from the theory to a more practical example, which is the Penryn Castle, where we installed such a system to trial it. So here on the left-hand side, you have Penryn Castle. The marker here is more or less where the kitchen is. The kitchen is somewhere here, I would say. But we show this aerial view because the heat to the castle is actually delivered by a biomass boiler building, which is more or less at the bottom here, close to the parking lot. And I say this because we will talk about electrical savings later, which are basically reduction in pumping consumptions from that boiler house here to the castle. And we have a situation where the kitchen is up here, the kitchen restaurant is up here, the drain flows down here and then under the coal yard here out. And so we installed the heat exchangers here. So we had the vertical drop available. We see a picture here of the heat exchangers. So the height of this drop, so from roof to floor here is around a bit more than 2 meters, and we observed drain water temperature with peaks up to 50-55 degrees. And there was a water consumption in the kitchen of around 650 liters per day. So based on those numbers, we proposed a few, let's say, modifications to the current drain system to recover the heat. So if you have the current drain system where the drain water flows through here, and then we have the fresh water coming in, either going straight to the kitchen for cold water use or going through the heating system for hot water use, we proposed actually 3 configurations for heat recovery. The first one is the classical system, let's say, where the incoming fresh water is preheated before it goes into the classical heating system. So this heating system here only needs to heat up from 25 to 60 degrees rather than from 10-15, and so reduce the fuel consumption of this heating system. Now, because we were concerned about these temporal mismatches between the availability of heat and the heat demand in the kitchen, we proposed a second system where we actually lead the fresh water into an intermediate buffer tank here and recirculate it through the heat exchanger the whole time. So we're sure to capture all the heat that is coming through the drain here, because at all times we have flow through our heat exchanger recovering that heat. When needed, the preheated fresh water is then again pumped through the classical, the traditional heating system. Our third configuration is basically combining both of them. So the first system was the simplest and thus the cheapest. We have some estimated investment costs. So for the first one, around 950 pounds, the second one, 1,900, and then the third one, 2,400, basically increasing the material that's used. And so then we made a pre-feasibility analysis and a simulation to see how much heat we could recover. And we are somewhere between 6.5 and 9 kilowatt hours per day. And we expect a reduction in the pumping from the boiler room ranging from, 15 watt-hour to 20 watt-hour per day. This coincides with financial savings ranging from 70 pounds per year to 100 pounds per year, and greenhouse gas emission savings from 35 to 50 kilograms per year. Now, this reduction in greenhouse gas emissions are quite small because we used the conversion factors for company reporting, where biomass, a wood chip, has a very low conversion factor. Now, the technical emission savings are a bit higher and are more in the order of magnitude of 750 kilograms per year. We still have quite a remaining uncertainty on the flow, as we discussed earlier. We then try to look at, so that was our theoretical assessment, let's say, our simulation, and then we tried to install it at Penryn Castle, and we operated the second configuration first. What we did that, well, we started with this one and were then basically halted by the COVID virus. And so we saw, sorry, we'll start here. We have, again, the kitchen up here and the heat exchangers that are installed there. So this is the horizontal drain, 2 heat exchangers here, and then I'll show here the electrical box because we had to avoid it. Was one of the additional complexities of the installation that had to be overcome. Here you can see a picture of our buffer tank and the different pumps and the measuring equipment before it was cleaned up a bit. And so basically we operated for 3 weeks, and the kitchen opened around 17th of February. So that's somewhere around here. And we saw an increase in temperature before entering the traditional heating system from around 12 to 17.5 degrees. Oh, sorry. That coincides with a heat recovery of about around 8 kilowatt-hour per cubic meter of wastewater. So, and this 8 kilowatt-hour per cubic meter of wastewater is typically the sort of data we use in the eco-design toolkit of the third part of this presentation. So using this second configuration of the heat recovery system, reduced the heat consumption of around 25%. But of course, we have some pumping consumption because of the recirculation pump and the feed pump to the kitchen. Now we have a corrected configuration 2 here, which is basically by placing a timer on the energy supply to the pump, so avoiding it to run overnight and making sure that it only runs during the opening hours of the kitchen. So in short, let's say, we have, by transferring this market-ready technology from showers to the kitchens, we estimate that around 89% of the recoverable energy in the hospitality and services sector in the UK can be recovered in a financially viable way. At the cost per kilogram of CO2 equivalent saved, that is several orders of magnitude smaller than for heat pumps. So this well-established technology can be transferred, but some questions remain about the distance between drain and heating system, the availability of this vertical drop, and it's not financially feasible at very small flows. So in that regard, the DWHR project is working on a grease trap heat recovery system. Let's say the first measurements started in August 2017, and then some lab experiments have been done, etc. And so this system is continuously under development. At Penryn Castle, we saw in 3 weeks of operation around 25% reduction in energy consumption. So that was it. Thank you very much. I'll stop sharing, John, so we can.
No, you could leave it there, Jan. Okay, actually, we'll leave it there for the moment, and we thank you for the timely presentation. Gives us a few minutes for questions, and I haven't seen anything coming in the chat yet. But if there's any posing comments, now is your opportunity to raise your hand. I'll happily invite you to turn on your microphone and ask a question of Jan on this case study and heat recovery. So Jan, obviously, while I'm waiting, obviously COVID-19 kind of led to a kind of a shorter monitoring period there, and early phase in the consumption of water in that kitchen. I'm assuming the numbers would have went up in the months after a busier period as the summer went on in terms of more potential.
Yeah, that's what we'd expect as well. We'd have more visitors compared to end of February. It's not the high season yet for the visitors either. So we'd expect more drain water flow and thus more heat recovery, at least in terms of volume for sure.
Yeah, and the opening hours of the kitchen was.
So in general, I don't have it in front of me, but I believe it's something. So it's also open for staff. So I think I'd say 9 to 5, but with a clear peak, around lunchtime.
Okay.
Because they have some meal preparation, but they also have let's say pre-packaged meals that you can get there, right? So it's not only restaurant services.
Yeah. So every type of kitchen would have different kind of flows of heat, large capacities for heat recovery, depending on what's going on in the kitchens. I don't see any questions coming up, so right. I don't want to hold Isabel back, and also then we can bring our break forward and have part 3 in due course. So Isabel, I will allow Jan, if you don't mind, handing over to Isabel for part 2, which is on environmental costs and savings of heat recovery.
Okay, thank you, Jan. Thank you, John. So I'm going to share my screen, presentation mode. Okay, I hope you can see it all right now. Please shout if not.
Yeah, that's perfect.
Yeah, so yeah, welcome to the second part from my side also, which is about environmental costs and savings of recovering heat. So you've heard from Jan now what the opportunity is on a national level, and also the example for the Penryn Castle case. And he has also talked about operational savings that we have in terms of greenhouse gas emissions. But there is another side to the environmental aspects of recovering heat. And what we haven't looked at yet is that with the equipment that we need, there is also an environmental footprint connected to that. So which I will call environmental costs in my part of the presentations, which come additionally to the savings, and which we have to consider as well if we want to look at what the environmental sustainability of recovering heat is. So if we want to look at the environmental costs or the environmental footprint of really any sort of product, then the methodology we can use for this is called life cycle assessment. Maybe some of you have heard about this already. And I'm just having my pointer option to laser pointer so you can see it better. So in a life cycle assessment, we look at all the steps of the life cycle of a product. We look at resource extraction, the processing of the resources, the manufacturing stage, the distribution to the customer, the use stage, and end of life. So what happens after use, which can be recycling ideally, but can be incineration or landfilling, and so on. And we look for all these stages of the life cycle at the resources which are being consumed from nature, so that they're entering our life cycle, and also the energy that's being used. And we're also looking at the emissions which are created at every stage of the life cycle, emissions that can go to air, water, and to soil. And in life cycle assessment, we categorize or classify these emissions according to the damages they cause. And we have a couple of different environmental impact categories. In life cycle assessment, of course, the most famous one is climate change. So that's the greenhouse gas emissions or carbon emissions, as they are also called. But there are other categories as well, which are a bit often a bit underrepresented in the discussions, which, for example, I'm just mentioning a few, is eutrophication, which is basically over-enrichment of, for example, soil or water with nutrients. We can have ecotoxicity, we can also have human toxicity, and we have resource depletion as well. And there are many, many others. Just showing you here basically that climate change or carbon emissions is not the only thing we look at in a life cycle assessment. And yeah, and the same, or this sort of life cycle assessment we do, of course, as well for the heat recovery system. So we start with the raw material extraction, which is needed for the manufacture of the heat exchanger itself, but we also have some fittings that we need for the installation. We have pipe work, so we need the pipe work to connect the heat recovery or the heat exchanger to the boiler and to the freshwater supply. We ideally insulate our pipe work, and then we need packaging as well, and then transport the parts to the restaurant, for example, where the heat recovery system may be installed. So all of this is included in a life cycle assessment and also in a study that we did. On the other hand, of course, as you've already heard now, we have environmental benefits, which come from avoiding the normal heat source, the normal energy source for heating water. And with these heat sources, it's the same. They have environmental costs, which we avoid in this case. And in our study, we looked at different options for this energy for heating water. We looked at natural gas, at grid electricity, at wood chips, which is the case also in Penryn Castle, at solar thermal energy, at geothermal energy, and also at the mix that's currently used in the UK. So our study was focused on the UK. The current water heating energy mix. So this is mainly natural gas, but also electricity and some other fuels. And yeah, and also all these, also the energy generation also has a environmental life cycle and footprint coming with it. But in this case, we're avoiding the footprint. So these are all benefits. And I'm just mentioning here what is also important to consider for renewable energy. Also here we have a footprint. Of course, that's not generated through combustion of fossil fuels, but in this case, it's actually the manufacture of the appliances that I need. For example, appliances for the solar thermal systems. So what we need to do in order to decide if heat recovery is overly sustainable is comparing the footprint of the heat recovery system with the safe or avoided footprint from the energy that we save. And we have looked at retrofitting commercial kitchens, so all the equipment you need for retrofitting. Yeah, it's not that easy yet. There are a couple of other things that need to be considered, or that on which our comparison, our results depend on. So the environmental footprint of our heat recovery system depends, for example, on the material that I choose for the heat exchanger. Now, the only commercially available heat exchanger is made from copper. And we looked in our study as well at what happens if I have different recycling rates for copper, for example. And we also looked in the study at an alternative material. So just mentioning this as a little preparation for when I show you the results. And then it also depends, the footprint also depends on which material I use for pipe work and also how long the pipe work is. And well, this is interesting because here you can actually choose what material you want to use. You can choose between copper, steel, or a plastic-based, for example, polyethylene pipe. And depending on the existing plumbing system in your or in a kitchen, you have a different requirement for pipe work depending on the distance between the drain pipe and the boiler, for example. And Our environmental savings, however, also depend on the kitchen itself, like on the size of the kitchen. And with the size of the kitchen, I mean the amount of wastewater that's created in the kitchen, of course, and the temperature. So this has also been considered in our study. So now let's go to our results part 1, where I'm now showing you the environmental footprint in detail. So a bit, where do the emissions come from and what are the hotspots for the footprint of the heat recovery system. The example I'm showing you is a heat exchanger from copper and also pipework from copper, both with a recycling rate of 35%, which is the average recycling input rate for plumbing appliances from copper in Europe. And this configuration, like this, was also used in Penryn Castle in the configuration 1, so the simplest of the 3 configuration and most useful one. And we had also there 10 meter of pipework. So what you can see here is the percentage of or contribution of the life cycle stages to different environmental impact categories. We will not look at all of them. This is more to show you that we did not only look at global warming potential, which is the first bar and which I would like to focus on for now. So what you can see here, so the brown part is the heat exchanger or the manufacturer of the heat exchanger, and the blue part is the manufacturer of 10 meter of pipework from copper. And we can see that this pattern is very similar across all environmental impact categories. And it shows us that the manufacture of these copper parts has the biggest influence on the environmental footprint. And just a bit of background, this comes from 2 parts mainly. So one is emissions from the mining stage, so from mining the copper ore, from producing the copper itself, but also from processing the copper, which needs a lot of energy for forming it, for example, and finishing it to the final heat exchanger or pipework. So this is the main impact. We can see that other stages, for example, transport is very minimal compared to this, also end of life, and the other parts we need as well play a minor role. With this, let's go to result number 2, where we want to compare the footprint of the heat exchanger, which we have seen now, to the pipework. We are again just focusing for now on climate change or greenhouse gas emissions. So I told you that we looked at a different material as well for the heat exchanger, which unfortunately you cannot buy yet for this type of heat exchanger at least, which is here the first bar. This heat exchanger or this material is a polypropylene and with graphite particles which enhance heat transfer. Then we have the emissions from the typical copper-based heat exchanger, and then we can see here the footprint we have for different options of pipework being used. So here polyethylene, steel, and copper. And we looked at different lengths of pipework. So the dark blue bars is just 1 meter, then we have 10 meters, and then light blue is if we would need even 30 meters. And what we can see here is that depending on the installation requirements really for a kitchen, it is possible that actually the footprint of the pipework is bigger than the footprint of the heat exchanger. So the lesson learned from this basically is that we should see which material we are choosing for pipework, and you can see polyethylene has the smallest footprint, and how can we minimize the need for pipework and maybe construct the system a bit more compact. Now let's go into actually comparing our footprint versus our savings. And the first results I'm showing you here are from our Penryn Castle case study. It's shown in environmental payback times. So basically the same as a financial payback times. So we have the costs from the life cycle assessment versus the savings during operation. And I'm showing you here the results for different energy sources which can potentially be replaced. Again, for the climate change category. So we have the years here on the left-hand side. And as you can see, and that's good news, our highest payback time, which is for solar thermal, is also under 2 years, and we expect our system to run at least for 10 years, or probably it can also, so according to manufacturer, it can also run for probably over 20 years. So what we can see here is that our payback time is way smaller than the lifetime of the system. So that's good news. And in the case of Penryn Castle, we used wood chips. And then I also want to show you the results of another environmental impact category. So here, as an example, it shows resource depletion. What we can see here, first of all, is that our payback time is much larger. So in the case of wood pellets, it's 33 years. So this shows us that for overall sustainability, it's also important not to look only at climate change, but also at other impact categories. So we can see here that in some cases, it can take quite long to offset actually the environmental footprint which I created in the first place through the production of the heat recovery system. And this is, for example, the place if either we don't recover a lot of heat, or we have the footprint of the heat recovery system is quite high, and our avoided emissions or avoided resource consumption is actually quite low, as it is, for example, the case with wood biomass. So in Penryn Castle, ideally, the system would be in place for 33 years. Now, coming to a more general comparison, where we can see how does this comparison look like for average UK kitchens. The results are shown in impacts per kilowatt hour. And we looked at different flow rates here, and also, again, different types of avoided energy. Here, the first graph, again, for the climate change category, shows us, first of all, the greenhouse gas emissions I have for producing 1 kilowatt hour of heat using natural gas, electricity, wood chips, geothermal, solar thermal energy, or the currently used energy heating mix. And then here on the left-hand side, the 2 bars, which are almost not visible, are actually the impacts we would have through recovering the same amount of heat. And we can see it's very, very low. And we have 2 different cases here. So the left-hand case is low impact from heat recovery, which basically represents a kitchen with very high flow rates, where I can recover a lot of heat. So my impacts per kilowatt hour are smaller. And then I have another example where I have very low flow rates and so a very higher environmental footprint for recovering heat. But the good news is that no matter if my kitchen is small or big, it's still competitive recovering heat versus using the heat from other resources. So even if I have renewable energy heating the water in my kitchen, it makes sense to recover heat. However, things can be a bit different if I look at, for example, resource depletion in this case. So now if you look at the red bar, which is a small kitchen case, then I can see it would actually make sense not to recover heat with the under the circumstances or conditions that we looked at here. We considered here a heat exchanger from copper and the pipework from polyethylene and a 10-year lifetime. So in that case, it could be actually better if I have natural gas or wood chips for my hot water production, that it's actually better not to recover heat. Also, we have seen in our study that this is really a minor part of, small part of the kitchens in the UK, which in which case it would not be overly environmental sustainable to do heat recovery. And we can see for climate change, sustainability is usually given, but not necessarily for other categories. We did an extrapolation of the potential greenhouse gas savings for the UK, where our study was based on, where we had all the data. So if we installed this type of heat recovery in all food outlets in the UK, then we could save approximately 500 kilotons of CO2 equivalent per year, which equals taking off 260,000 cars off the road. And so I come to my conclusions here. So from an environmental point of view, we can say that on average, so really on average, it is sustainable from a water consumption of approximately 170 cubic meter per year to do heat recovery. If we look at the current water heating energy mix in the UK, and if we look at the system that, for example, needs 10-meter pipework, so an average system, this equals approximately 500 kilotons of CO2 equivalent. It's important to increase the savings for smart material choice, if possible, for example, with the pipework and the compact design. And environmental sustainability is usually given for carbon emissions, not always for other emissions like resource depletion. However, we can say that affects from, on average, only about 10%, where it might not be sustainable. So it's still, in general, it's still very good news, even though we have some smaller kitchens where it might not be viable. Okay, John, do we have time for some questions?
Yeah, thank you very much.
Do we have
I think
any?
we're nicely on time, Isabel, and I think you've highlighted a dimension that a lot of people don't consider beyond maybe this potential heat recovery, that we can do things more sustainably even in the design process. So I think, thank you. Is there anyone who wishes to pose any questions to Isabel? And please, that I've been looking at the chat, it seems quite quiet, and please don't be shy, but please, if you want, in the reactions, you can raise your hand or even just turn on your microphone. We don't have too many people, that the likelihood of people all jumping up at once. So, and Isabel, just a comment while I'm giving a moment for everyone, if there's any questions being formulated. So you note here 170 cubic meters per year consumption. So earlier Jan mentioned about 2 cubic meters a day was the kind of the threshold. So really, 80 or 90 days per year of the 2 meter cube per day makes it sustainable. So it's very much a feasible option to make it sustainable for a year as well. Which is great. Jenny had a question. Jenny, could I invite you to, I noticed Roberta's commenting that Jenny has a question. Jenny, do you want to turn on your microphone and ask the question? Or was that for Jan? I think that was for Jan, perhaps.
I believe there was a question on the estimated cost, but I suggested to wait with that for the eco-design toolkit.
Okay.
Because there we look at payback periods and
yeah,
things
I think,
like that.
Jenny, do you want to ask a question now? I think you're.
Yeah, sorry. Hi, can you hear me?
Yes, please go ahead.
Sorry about that. You can tell I'm a technophobe. It was just a quick one, like Jan said. Sorry, I know I was a bit of a keen bean there, because I know you may well cover this. I was just looking at it in terms of financially what the cost was for implementing a heat recovery system like that, and just if you had any recommendations of local suppliers in Ireland who would carry that out. But that might be covered, so we can wait, whatever works.
Jan or Isabel, do you want to kind of provide any kind of brief response to that perhaps at the moment?
Yeah, go ahead, Jan.
Yeah, I can.
You've done the installations as well.
Talk about the installation we did at Penryn. So the cost of the heat exchanger itself, I believe, is around 390 Great Britain pounds without VAT, value-added tax, so without VAT.
Okay.
So on top of that comes like the additional kind of supplies we need, and the labor costs.
Yeah.
So I believe we estimated around 900, a bit more than 900 pounds for Penryn Castle.
Okay.
But that's would be in case we only install configuration 1 and we installed the 3 configurations, right?
Yeah.
As in terms of supplier, I don't know if we're supposed to make advertisement, but
Yeah.
there is a company in Northern Ireland that we got it from a company in Northern Ireland that imports from the Netherlands, and it's a Q-Blue system that was bought in Northern Ireland at Shower Safe, they're called.
What are they called? Sorry, Shower Stage.
Shower Safe. But there are other systems. There are other suppliers that supply similar systems.
Yeah. Yeah. No, I'll look locally as well. That's really helpful. Thank you. So it's
But
roughly about 1,000.
But they are based in Northern Ireland, I believe.
Cool. Okay. Thanks very much. Cheers.
Thank you, Jenny. If there's no other questions for the moment, then I think a deserved break for everyone wouldn't be a bad idea. I'm noting my time as 13:57, and so I was going to suggest a 5-minute break, but just to try and maybe give you a little bit more time, I'm going to suggest that we all return at 5 minutes past. So just over a 7-minute break for everyone, if that's okay. And then we will provide you with details and information on our heat recovery tool, where you can actually do some financial number crunching. And I think, Jenny, you might find that quite useful. And Isabel will give a kind of a run through of the tool, as well as sharing it in the chat for you all to download and to utilize beyond today. So thanks very much, everyone, for joining for part 1. We'll have a 7-minute break and we will return at 5 past the hour. Chat to you all then. And thanks to Isabel and Tian for your presentations in the first half. So speak to you all in 7 minutes. So we'll begin in 1 minute, just to give you a kind of a 1 minute warning that we'll return in 1 minute. So welcome back, everyone. I hope you had a break where grab a coffee or just stretch your legs for a few minutes. And thanks for staying with us for the second half of today's session that's going to be led by Isabel in a moment. And this really is to kind of provide you with an insight into the tool that Isabel has developed to try and provide you with a kind of an economic and an environmental costing of potential installation of a drain water heat recovery system. So how this half is going to go, when I hand over to Isabel, she'll kind of give you a guide through the tool. In this half, I encourage you to raise your hand or to drop a question into the chat at any time throughout the session. It's going to be as interactive as possible. So we prefer if you raise your hands and I'll come to you to invite you to ask a question, especially because we're going through this tool live. Roberta from our team has provided a link in the chat. So if you have not noticed, it's been placed there during the break, and you can download that simple Excel file that you can use yourself. Isabel's going to be going through an Excel file on screen in a few minutes. So if you have the luxury of 2 screens, you could perhaps have the Excel, your own personal version on your other screen and go through it. But we would encourage you to kind of keep visible of what Isabel's going throughout the session to make sure we get as many questions and clarity. We can provide as much clarity as possible. But before we do so, Isabel, you want to do another poll?
No, that's for after the toolkit.
That's for after. Well, then, in that case,
okay.
I will stop sharing and hand over to you.
Okay, great. I hope you were all successful in downloading it. You don't need to open it yet. You can also just follow my virtual tour first. I'm going to share my screen with you. Yeah, if you had problems with opening it or anything, then please let us know. But so far it's calm, so that is good news. You should be able to see my screen now, my Excel screen.
Yeah, that looks good, Isabel. Go for it.
Okay, very good. So when you open the toolkit, what you will see first, is our little introduction slide. Just a little bit of background. Who is behind the tool, which you all know now. Also here, the funding that has been kindly provided. So we then, after this welcome slide, you just click on through the tabs here below. So the next one is the introduction. I mean, most of these things you know by now because you have heard this now presentation. So just a quick recap: who is this toolkit made for? So everybody who's a manager, owner of a commercial kitchen, or just interested in this. So it's especially for for all sorts of commercial kitchens. Really, can be a restaurant, a pub, a canteen, a cafe. Can be a kitchen in a hospital or in a care home or in a school, for example. And this toolkit shows you what you need for the installation, and then financial and both environmental aspects are included in the toolkit. So on the financial side, we take into account the capital costs of the heat exchanger, the fittings, the pipework, and pipe insulation. And the results you will get are operational savings, investment costs, and simple payback time. And then going to the environmental aspects. So of course there is the footprint of the environment of the heat recovery system included, which I've talked you through. And also here it's the same, it's all the equipment taking into account. And the results you get are the operational carbon savings, but also the carbon costs, so the footprint of the equipment and the payback time. And we will also show you a couple of results to other environmental impact categories other than greenhouse gas emissions. And in the end, you're hopefully able to understand better if the kitchen, your own kitchen or a kitchen you're looking at could be suitable for drain water heat recovery from both a financial and an environmental point of view. So the next step then introduces you to the heat recovery system. This now is probably not new to you anymore. Tells you, for example, that we unfortunately need this drop of the drain pipe of about 2 meters to be able to replace the part of the drain pipe. And then here a little graphic again explaining what Jan has already explained, and here also showing the pipe work which we need to connect to cold water supply and to the boiler. So we assume for a baseline scenario that the system is in place for 10 years, but the lifetime of the system is longer. So you will be able to play around with this number. And we also assume for the base case that the pipework is made from polyethylene, but also this you will be able to change. And then we come to the data entry field. The first question is about your water use, and you can here choose between either filling in the left side or the right hand side depending on the data you have. And don't worry if you don't have any data today, because when you click on this question mark, then you will get some more information and also of the typical values you can insert here, so you can play around with this. So you can either decide between filling in the water consumption of your kitchen in cubic meter per year, and if you don't have this information at hand, it might be easier for you to fill in the right hand side, which is the number of meals or covers per year and the type of location you are. And here on the question mark again, you can see what category your commercial kitchen would fit in. So for example, if you're a care home or hospital, then choose the category restaurant. And then if you click here, you will be able to choose. And then in the second part, we ask you about opening times. So the number of weeks you're open per year. And then you can choose if you want to enter weekly opening time in one number, or if you want to fill in the hours per day separately. The next section is about your current energy source, so about the savings basically. You choose here the current energy source for water heating which you're using, and you can choose between natural gas, electricity, green electricity, light fuel, oil, wood chips, solar thermal, and geothermal. And then you choose your country. So because our project area is Ireland and Wales, it's specifically designed to fit the UK and Ireland. So you can choose this. If you're not from any of these regions, just decide for one. And then you can enter here the price for water heating that you're currently paying. The last question we have is the approximate distance between the kitchen drain pipe and the boiler, which is necessary to estimate the pipe work which is needed. So you might not have this information at hand, but we recommend to play around with numbers between 5 and 10 meters, which we see as a realistic case from our experience. So I would say I just fill in some sample numbers, so you can also see some sample results already. So let's say we have 1,000 cubic meter per year here, for example. We are open 40 weeks per year, and our opening time are 30 hours per week. And then let's assume, so at the moment, the most common source is natural gas. Let's assume we are in the UK. And I've done some research on this, but probably many of you are rather experts in what the prices for for gas. So correct me if that's not realistic, but I found something like 6 pence as being realistic for commercial consumers. Yeah, and as a distance, let's just put 5 meters for here. Yeah, and then we can go to our results sheet. So it's organized in a couple of parts. So we can here see in the green part, this is our carbon savings. On the left, on the right, the yellow part is the heat recovery potential. And then if we scroll down, we get to the financial results. And here in our dark green box, we have some more environmental categories. So just looking at this example, we have here, for example, 2,000 kilogram of CO2 equivalents, which you would save per year, which equals 16,560 kilometers of car transport avoided. This times 10 because we have a service year of a service life of 10 years considered here. Is our total operational carbon savings. We can see that our carbon costs are quite small compared to this, which then gives us a carbon payback time which is less than a month. And we can see here in this graph also the comparison between the baseline and custom values. So here on the top we can change the lifetime of the system, for example 15 years, and we can also change the type of pipework we're using, the material. So here in this section where we see more about our other environmental impacts, so we have more impacts shown as payback time. This is the payback time as I also used it in my presentation. We can see here, okay, nothing more than 4 years. I run my system for example, 15 years. So that's all good. It's all paid back. So for example, here, this is resource depletion. We can see if we change the material to copper and we scroll down again, we can see that our payback time has risen, and we can see that approximately half of our impacts are caused by the pipework. So this is what we can see in this part. And then here in the left, in the yellow part, we can see the heat recovery potential. So this would be per year about 7,000 kilowatt hours and 77,000 during the lifetime, or for 15 years more. And then looking at the financial assessment, we would in this case save about 460 pounds per year, or 4,600 pounds over a 10-year lifetime, or more during a 15-year lifetime. The investment costs in this case would be about 1,000 pounds. So the toolkit also takes into account that is if I have very low rates, that I do need more than one heat exchanger. And our simple payback period in this case would be 2.3 years. And if I choose copper, then it would be a bit higher because copper typically costs a bit more. And in the orange box, you find some overall conclusions. So this case looks very good, both financially as well with the carbon emissions and also the overall environmental impacts. Okay, first of all, are there any questions by now? Because now it would be your time to open it, play around with numbers, either real world numbers or invented numbers.
So Isabel, there hasn't been any questions yet or raised hands. I would encourage anyone that does have any queries. So if we did have an example, though, you have an example of relatively small installation, is it? Like if we went back to the previous tabs?
So it's like middle, I would say. So it's not small.
Yeah. So if
it's
I
not
was
a small one, but there are also much bigger ones. So what we found from the data that we got on commercial kitchens in the UK, it can be typically something between 200 and 4,000 cubic meter per year. But obviously there is no limit, not in any direction. Yeah.
So we do have a question, a raised hand. For some reason I cannot see it, but thanks, Roberta. Camillus, do you have a question for us? Please turn on your mic, more than welcome. I see your microphone's on, I just can't hear you. Yeah, I'm afraid I can't hear you, Isabel. No?
Maybe if she can just post it in the chat.
Yes, Camillus.
Oh, for you.
Okay, Isabel, a quick question for you. Does your toolkit take into account the different efficiencies of the different types of heat exchangers? Like we've carried out a number of projects in this area, and we've used stainless steel mostly. But I was very interested in your polyethylene with impregnated with some sort of conductive material impregnated in polyethylene. Does your toolkit take into account, or does it assume a certain level of heat exchanger efficiency?
Thank you for your question. So in the toolkit, we are only taking into account the copper heat exchanger, because this is the only heat exchanger which is commercially available for this application at the moment. And the efficiency or effectiveness data of heat recovery are based on the monitoring studies that Jan did with a couple of real world examples or real kitchens.
Okay,
so
good.
It's an average of the effectiveness of heat exchange, the heat exchange, the effectiveness of the heat exchanger is also given by the manufacturer, and then the data, the information of how much heat can be recovered is based on the monitoring study. So based on temperature and flow data that have been measured in these examples. Yeah, Jan, if you want to add anything, please go ahead.
Yeah, maybe just to add that there is an impact on there is an impact of the flow rate on the efficiency, and that has been included in our assessments. So it goes up until let's say the design flow rate, and then stays constant for a while, and then drops back off, and so that has been included in our studies.
Okay, thank you. It's very impressive, very interesting, and I think every kitchen should seriously consider installing these. We're in the leisure industry, and we've carried it out on where pool water is used when you backwash a pool to clean the water. About 5 or 10 cubic meters are spilled in the space of 5 minutes, and it's an awful waste for that to be thrown into the dump. So we've installed heat exchangers in many of our sites, and we work it out to be about 5-year payback. Okay, I'll switch off now, will I?
Yeah, thank you very much for your question, and it's great to know that this application is taking place. Now, I didn't see your hand up, and I don't know if there's anyone else. So Roberta, if you're in the background and you can see it that I can't, please do. Isabel, you're no longer sharing your screen, I note.
Yeah, so I thought if
there's any more questions
for playing around with it on your own, if you like.
Yeah, by all means. I would be curious, actually, based on Camillus' example, to put in from 1,000 to 10,000 to kind of talk about that 10 cubic meter that he mentioned, just to see what sort of payback is for the larger scale for those that might be just interested. So if you can share the screen.
Yeah.
An example of that larger extreme, let's just see what the carbon and financial payback is for everyone. And again, if there's no more questions or comments coming in, we'll probably move on to the poll in a moment, I think.
What we can also do, I would be interested if there is someone who has real world data from a restaurant kitchen, then we could also try this out here live.
Yeah,
either the participant could share his or her screen, or I can enter the values here for everyone to be seen. Well, we can try with the 10,000, although I'm not sure if that might crash the the toolkit, because this is not what we have considered to be. But let's see, we can try. And I just leave the other things as they are. No, it works. Awesome. Well, it's just 10 times what we have seen before. Probably the amount of heat exchangers that we would need is a bit too low, because the maximum we had for kitchen water use was 4, so maybe you would need a couple of more here. But the heat recovered, so this is definitely
substantial.
Yeah, a good estimate and a valid estimate with this toolkit. So
yeah, and definitely
10 years.
And
then if we look at finance,
from your presentation, modifying the material can have a significant impact on some of those scores as well in relation to your customized versus baseline. So I don't see any hands up, and I don't know if it's my system's not picking up on that. Roberta, there's nothing, no hands up.
No, I know, I can't see any.
Okay.
Is there any kitchen user, manager, owner amongst participants who
would have some theoretical data as well? We don't need precise numbers. Again, maybe you don't want to share. We can understand that. Okay, no, I don't see anything. Again, I'm aware that we set 2 hours aside for this, but there's no need for us, Isabel, to kind of drag this out. I think everyone's got the tool, and the great thing is your email address is on the front page of this tool as well. So people can contact you with queries with regards to that. I think it might be worth doing the poll to get feedback, and then we can come back to this if someone ends up having a question that we need to do a demo again. So I will share my screen on the poll, but again, if you want to throw the question out to everyone regarding the toolkit, what did you think of it?
Okay, thank you, John. So I'm going to launch the poll. But I need the second poll, relaunch poll.
So while you're preparing, just to note for everyone that's here still, Roberta in the chat has also put a feedback form around this webinar, because we're keen to hear from you in regards to the workshop and how we're doing, so to speak. Was it clear? And it'll only take a moment at the end of today's session. So
okay, great. So I'm launching the poll now.
Yeah.
So first question would be on how user-friendly did you find the data entry? The second one on how did you like the results section? So maybe there was too much or too little information in this, or too complicated. And then we would also be interested if you could think of recovering heat in your business. So especially if you're a hospitality business as well, if that looks like something feasible and interesting for you. So I can see that people are voting, so I'm just giving you some more seconds. Okay. I can see about 35% have voted, so I'm waiting a bit more.
So Isabel, there's been comment from Camillus in the chat to just add some details on the assumptions in the tool for maybe a next iteration of it, so they can adapt it to individual sites. So we can look at that. Yeah, thanks for the feedback on that.
Yeah, thank you for this. I mean, I haven't read through all the information that I gave, like all the text that is in the toolkit. So there's a bit more background information that I have told you about. But I agree, it could be very interesting to see what the numbers are based on and how we did the actual calculations. Because the calculation tab, which looks a bit more complicated and that's hidden at the moment, so it might be worth. Thank you for this input. So I can see 76% have voted, and I think
that's good.
That's good. I will end the polling and share the results, which you're hopefully able to see now. So how user-friendly did you find data entry? So most of you said it was easy and straightforward, but some parts were maybe not clear. So I think that's a good start for a discussion, and I would be very happy to hear more about what we could change here or what was not clear. So please shout or raise your hand or put your question in the chat. Then how did you like the results section? Enough results and well explained, half of you. But again, here I think not everything was completely clear. So I think that's again a good reason to discuss a bit more in detail. And then, do you think you could recover heat in your business? So okay, half of you, yes, this could work for me. 20%, I don't know enough yet. So please pose your questions again. Maybe that savings are marginal compared to overall spending. Yeah. And no, my results were so bad. Yeah, I mean, if that person is interesting to tell us more about his or her case, that would be also very, very welcome. Yeah, I think this is a good start for more of discussion. I will stop sharing the results.
Thanks, Isabel. So I'm going to move on to the questions and feedback slide. But as I do that, I've noticed two comments just to address two people, and I think Roberta has responded in the chat, but I want to make sure that it's clear. This is recorded, this webinar, and we will be sharing details of how to access that recording for those of you who had to leave early, or well, it's too late to tell you that, or for those who have joined a little late. We have a membership section on our website that will store not just this webinar, but the past webinar. And we would appreciate if you'll receive the email tomorrow to follow up on that. But also, please do share this with people who you might feel they're interested in. Just because they didn't participate in today's session, doesn't mean they can't access our membership, free membership, I might add. Section of the website to access these recordings and indeed access the toolkit. Camillus also made a comment. You might have connections for us that might be interested in the work. Yes, that would be really appreciated if you want to respond to us. And the email's actually on the next slide, Camillus, or we'll be sending an email via the DWHR2 email. That would be fantastic. So is there any questions for Isabel around the tool? I think we've had a little bit of feedback here in the chat, but if anybody has raised your hands, again, please, Roberta, I don't see hands up my function if there's some issue there. But Isabel's happy and welcomes any questions. Claire's appreciative of and Camillus are appreciative of the tool and for the informative nature of today's session, not just by you, Isabel, but also by Anne. Okay, Claire, thank you. That's a very clear comment about accessibility of the tool, Isabel. Claire mentioned dyslexia, and I suppose all these and acronyms get confusing. And I'm not going to lie, even someone who works in life cycle assessment, and we use abbreviations all the time. I totally get that. We speak our own language. That's something definitely. And thank you, Camillus, for the comments.
Thank you for the comment.
Yeah, and thank you.
I mean, the abbreviations should be explained in the toolkit, but of course I went maybe a bit too quickly through them, I admit.
So we're not getting really anything, and I don't want to delay everyone. I'm getting positive feedback, and we welcome your emails, and maybe we'll wind down for today, and I'll just complete the session in the next 2 minutes. And basically, this is what's key. Maybe if you have a second to take down these details. Now, Isabel's email will be shared, our contact details will be shared tomorrow anyway, and Jan's. But also Maru and Ajit, who are 2 members of our Trinity team, also work in this space and are happy to help. So, you know, we're a large team of researchers, and we're all willing to help out in this heat recovery space. So by all means, please get in touch for an individual assessment. We'll help you with the tool. Isabel will be happy to hear from you, as indeed the team will. So please do get in touch beyond today. And yeah, once again, Isabel, thank you very much for that. And Jan, if you're still there, thank you very much for today. I think the tool launch, if you will, is going to help people actually capture the feasibility of this and make it real, especially within the economic and environmental sense. So just to kind of conclude for today, we are not just a website. We've got Twitter and YouTube for information, for sharing what we do, our team, and kind of an insight to the greater project. But the website has lots of information and links for everything. And please do consider joining our Smart Specialization Cluster. It's a way we're trying to share knowledge in Ireland and Wales, and indeed beyond that. And so if you join, there's no cost. It just allows us to keep you updated and access to things like these webinar recordings. So I suppose our project wouldn't exist without our funders. Again, Ireland, Wales, Interreg funding, which is partly funded through the ERDF, or European Regional Development Fund. And they have supported us for the last almost 4 years, and we're around for another 2 years as well to continue this message of energy recovery in heat and hydro and various other ways to improve the sustainability of water supply and consumption. So don't forget, I suppose, that we're not done with our webinars, and we have one left, and one of our last 4 on benchmarking water and energy efficiency. So if you're interested in that, visit our website, sign up to that in the free sustainability webinars, and also keep tabs on what else is coming throughout the project. So once again, thank you very much, Isabel. Thank you very much, Jan. Thank you to those who participated for this afternoon, for those who attended, and have a very good rest of your afternoon. Take care, and bye.
Bye, thank you.
Thank you.